Hello, I'm Henry Talbott, and I'll be talking about eigenvalues, eigenspaces, and geometric intuition. Let T be a linear map from Rn to Rn. An eigenvalue lambda is simply a number that satisfies TV equals lambda v for some vector v in Rn. Geometrically, what this means is that if we take v and apply t to it, v will be scaled by lambda, but crucially, the direction of v will not change. We can also look at the eigenspace of lambda, which we'll define as E lambda. This is the set of all vectors v in Rn such that TV equals lambda v. In other words, these are all the possible vectors we could choose to verify that in fact lambda is an eigenvalue of T. Normally, finding eigenvalues and eigenspaces requires factoring a characteristic polynomial. But sometimes we don't need to do that. We can use geometric thinking to find the eigenspaces directly. And that's what I'll be talking about today. I think a really good example to look at is the reflection map. So let T be the map from R squared to R squared that reflects the plane around some line intersecting the origin, as we see here. What are the eigenvalues and the eigenspaces? Well, we can notice that since everything is reflecting around this line, the line of reflection itself is unchanged. For any vector v on the line of reflection, we'll have that T of v equals v. It just is reflected to itself. This corresponds to the eigenvalue lambda 1 equals 1, and the eigenspace is simply the line of reflection. On the other hand, if we have some vector perpendicular to the line of reflection, we can notice that it's flipped around to its negative. It reflects to its negative. Tv equals negative v. This shows that lambda 2 equals negative 1 is also an eigenvector, and the eigenspace, E negative 1, is the line perpendicular to the line of reflection. So why is this useful information to know? Well, it makes it much easier to calculate TV for any vector v in R squared. So start with some vector v. We can project it onto the line of reflection, and we can also project it down to the line perpendicular to the line of reflection. This gives us two perpendicular vectors that add up to v, since that's what a projection does. So what does T apply to these vectors? Well, T applied to the first vector, parallel to the line of reflection, just leaves it where it is. And T applied to the second vector, perpendicular to the line of reflection, will flip it around to its negative. So we have these two perpendicular vectors, we apply T, they flip around like that. Therefore, we can add these two new vectors back together to have T of v, which in this case is the dash vector that's roughly pointing upright. Notice that we didn't really have to do anything fancy. We said take two vectors, scale them, in this case scaling by negative 1, and add them back up to get our new T of v. Let's add some more notation. Let u1 be a unit vector that's parallel to the line of reflection. And let u2 be another unit vector that's perpendicular to the line of reflection. These two vectors are perpendicular, therefore they're linearly independent, and they form a basis for R squared. This means that for any v in R squared, we can write v equals au1 plus bu2, where a and b are simply a pair of real numbers. This is kind of the same thing we were doing before when we took projections. So this actually makes T of v really easy to calculate. So we have v equals au1 plus bu2. T is linear, so we can look at each term separately. T of au1 is simply au1. It's just fixed where it is. Well, T of bu2 is flipped around to negative bu2. Therefore, T of v equals au1 minus bu2. If we think of AB as being the coordinates of v with respect to the basis u1, u2, T maps these coordinates to a negative v. And in fact, this corresponds to the matrix 1, 0, 0, negative 1, sending AB to a negative b, or alternately xy to x negative y. Notice here, really importantly, this matrix is with respect to the basis u1 and u2, not with respect to the standard basis. And in fact, it's choosing this basis really precisely and choosing it in accordance with the eigenspaces that gives us this nice diagonal matrix to describe how our coordinates transform. Notice also that this matrix 1, 0, 0, negative 1 is precisely equal to lambda 1, 0, 0, lambda 2. It's precisely the eigenvalues that tell us how to scale our vectors when we apply T. And this actually extends to a much more general result. In general, if T is a linear map from Rn to Rn, such that Rn has a basis of eigenvectors for t. For any v in Rn, we can decompose it into a weighted sum of those eigenvectors because they form a basis. Applying t simply then scales each of those eigenvectors by some eigenvalue lambda I. Therefore, if we write, say if we use the weights as coordinates, so we take coordinates with respect to our eigenvector basis, when we apply t, we'll simply scale each of those coordinates individually. But this precisely corresponds to a diagonal matrix. And in fact, the diagonals will simply be the eigenvalues. This shows a really close connection between eigenvectors and eigenvalues and eigenspaces. And in fact, in particular, having an eigenvector basis and being able to find a basis for Rn such that T has a diagonal matrix with respect to that basis. Thank you.